this recording, we are going to propose a hypothesis titled Measuring NMR Spectra of Zero-Spin Nuclei. And it's important for us to emphasize that this is a hypothesis that we made and published in an article that you can see in this image. Two starting remarks, or three starting remarks. Why in English? Because we need this hypothesis to be known as extendedly as possible. Second, in this video, there will be a lot of talking, a lot of text. Three, if you are not in the fields of chemistry, physics, or radio medicine, I think that this video will make a very little contribution for you. And maybe fourth, if your English is not around more than medium, it will be tough for you to understand this presentation. Anyhow, let's move forward. NMR spectroscopy is one of the most powerful analytical methods. Along with its crucial uses in chemistry, it has extremely wide applications in all science fields and medicines such as MRI therapy, MRI imaging. With the current knowledge and technology, it is not possible to measure NMR spectra for zero-spin nuclei. This is a severe limitation for the analytical method itself, and more important, to science, technology, and medicine. In this communication, the article that we published is a short communication. We proposed theoretical basis for activation of zero-spin nuclei, and consequently, as a result, enabling NMR spectra of compounds that contain zero-spin nuclei. To demonstrate the severity for this limitation, let us consider the case of an isolation or laboratory synthesis of a new natural product. Suppose that this compound has very low concentration in its source, in the plant or whatever. Since the compound is new, it has to be characterized with several analytical methods with at least hydrogen and carbon NMR spectra on the top of them. As for H1, this is easy and possible since this isotope is the most abundant of hydrogen isotopes, around 99.99%, and it is non-zero spin. It is half. As for carbon, the situation is entirely different. NMR spectrum can be measured only for C13, also with nuclear spin of half, but with natural abundance of 1.03%. The most abundant carbon isotope is C12, and it is 98.97%. But with a nucleus of zero spin, means I equals to 0, this means that measurement of NMR spectrum cannot be done, cannot be measured. We hypothesize that using polarized radiation instead of the non-polarized radiation normally used in this method will activate zero-spin nuclei, induce spin split, and enable NMR spectra measurement. It is shown in this figure. If you take zero magnetic spin and you apply magnetic field, no splitting, no NMR. If you take non-zero and you radiate it with NMR radiation, there is a splitting, and this enables the measurement of NMR spectrum. Now, if you go back to zero magnetic spin, we hypothesize that if you radiate it with polarized radiation, it will split the spin, and this splitting will enable NMR spectra measurement. Now, as for the scientific justification, the interaction of light and matter is one of the most important phenomena in science, and it had been utilized in numerous scientific fields. One of these fields is optical activity detection with polarized light. In its most classical occurrence, plain polarized light interacts with a chiral center, and its plane of the light rotates in a specific angle. The most common case is the interaction of polarized light with two compounds with asymmetrical carbon, means a chiral center. We call these enantiomers in chemistry, resulting opposite rotations. These rotations are named specific rotations or angles, and they can be experimentally measured or theoretically calculated. But the presence of a chiral center is neither sufficient nor necessary, since chirality can emerge from other sources. On the top left, you can see the structure of the two enantiomers of alanine, the amino acid, and you can see that there is a chiral center, means a carbon atom attached to 4 different groups, and these enantiomers are mirror images, and this is the classical case. But if you look at the other structures, you can see that the mirror images can emerge from the structures themselves, which do not contain chiral centers, which do not contain asymmetrical carbon. So the presence of the asymmetrical carbon, the chiral center, is neither sufficient nor necessary. What does the work really is the polarized radiation. Moreover, it is now recognized that new forces involve not only the chirality of the system on which they exert their mechanical action, but the chirality itself of the optical field that generate them. Finally, it was recently reported that polarized light can polarize spins of electrons in indium selenide. We do not have the mathematical or physical formulation yet. But in conclusion, considering the presented above properties of polarized light, there is a logically based probability that polarized light can activate zero-spin nuclei and enable measuring their NMR spectra and other uses like MRI. Thanks for watching.